Hello viewers, today I am going to discuss oscillations in LC circuit. So let us start. If a charged capacitor is short circuited through an inductor, what happens? The charge and current in the circuit oscillates simple harmonically. So let us study this oscillation. The physics behind it. In capacitor plates, the energy is confined in this electric field when it is fully charged. Now what it does? It discharges and current flows through the circuit and energy is transferred to this inductor. When the capacitor is fully discharged, the energy confined in the magnetic field of the inductor supplied to the circuit and the capacitor plates again charged but in opposite direction. So let us study the mathematics. These are the two circuits. The first circuit is the capacitor plate is fully charged with Q0 and now the switch is closed and here the capacitor starts discharging and a current flows through this circuit. This current induces magnetic field in this inductor and energy is transferred from this electric field to this magnetic field here. At T10, as the capacitor is fully charged, the potential difference is V0 equals to Q0 C. So here the potential difference across the capacitor is equal to the potential difference across the inductor. Now this potential difference across capacitor is Q by C and voltage drop across inductor is L di dt. So I is minus ddt of Q because charge is discharging, the capacitor is discharging and the minus sign tells this. Now change of current di dt equals to minus d2q dt2 and we rewrite this first equation as q by c equals to minus l d2q dt2 and rearrange this d2q dt2 equals to minus 1 by lcq. This is the equation of a simple harmonic motion. So this equation we compare with standard SHM equation d2x dt2 equals to minus omega square x. Comparing we get omega equals to 1 by root over LC. And the solution of this differential equation we get q equals to q0 cos omega t plus minus phi. If the initial phase is 0, then we can simply write q equals to q0 cos omega t. And the frequency f equals to omega by 2 pi equals to 1 by 2 pi root over LC and time period tau equals to 1 by f equals to 2 pi root over LC. Now here is a comparison between the electric oscillation to the mechanical oscillation of mass spring system. Okay, as at time t equals to 0, the capacitor plate is fully charged to Q0 and the current flowing through this circuit is 0, right? The same situation is compared here with the spring of spring constant K of mass M. The mass is not moving when the string is stretched, but it is displaced with amplitude A, right? Now at the second cycle, when capacitor discharges, the current in the circuit is maximum. Similarly, the body of mass M is moving with velocity, maximum velocity due to the restoring force of the spring. Now in another cycle, when the current is 0 and the capacitor is reversely charged, the spring is fully compressed and the mass velocity of the mass is 0 and its amplitude is a, right? So we are comparing this amplitude with the charge and velocity with the current and the process rotating, right? So this is a analogy of oscillation of charge in LC circuit to a mechanical spring mass oscillation. Now their graphs. The charge oscillates sinusoidally and the current correspondingly it also oscillates sinusoidally. Now the potential energy in the capacitor it also oscillates sinusoidally, q square max by 2c, and potential energy of the inductor is half Li max square. This is the oscillation graphs. Now we study a numerical problem to be clear of this oscillation. So the problem reads, a capacitor of capacitance 20 microfarad is charged to 300 volt, right? It is then connected across a 10 millihenry inductor. The resistance in the circuit is negligible. Okay, the circuit, the resistance is negligible. So there is no heat dissipation. Total energy is constant. Total energy means the sum of potential energy of the capacitor and the inductor. Now we shall find the frequency of oscillation in the circuit. Very easy. Just compare this equation and put these values, and then the potential difference across the capacitor and magnitude of current in the circuit at a time 1.2 millisecond after the inductor and the capacitor are connected, and then magnetic energy and electric energy at two different times, at the starting time equals to 0 and at time 1.2 millisecond. At the starting time the potential energy is fully that of capacitor, but at a later time the energy is distributed among the capacitor and the inductor. So let us solve the problem. The frequency of oscillation is 1 by 2 pi root over LC. After putting this value we get frequency is 318.3 Hz, and the charge Q0 is C V0, and C is 25 microfarad and V0 is 300 volt, and we get the initial charge Q0 equals to 7.5 into 10 to the minus 3 coulomb. Now at time 1.2 millisecond the charge is Q0 7.5 into 10 to the minus 3 cos 2 pi, the value of the frequency 318.3 Hz, and the time 1.2 millisecond, and calculation reads minus 5.53 into 10 to the minus 3 coulomb. Next, the potential drop across the capacitor is Q by C, and it is 221.2 volt, and the magnitude of the current Q0 omega sin omega t. So we put this value Q0, that is we previously got, and 7.5 into the 10 to the power minus 3 coulomb, and then value of omega 2 pi f and sine 2 pi f and t. So this calculation leads to 10.13 ampere. Now at two different times the total energy. At time t equals to 0 there is no current in the circuit, so the potential energy across the inductor is 0, and the total energy is that is confined in the electric field of the capacitor is half q square by c, q0 square by c, and after putting the numerical values we find uc equals to 1.125 joule, and here this is the total energy of the system also. Now at a later time 1.2 millisecond we find the potential energy of the inductor half Li square, and after putting this value we get the potential energy 0.513 joule, and the potential energy of the capacitor is half q square by c, and we get numerical value 0.612 joule. So this value and this value, when they are added we will get the total energy, right? So total energy of the system is constant. provided that there is no heat loss due to the flow of the current in the circuit, or the resistance of the circuit is 0. I think you have a clear concept of LC oscillator, and so thank you for watching this.